have birds here, and apparently I'm deaf to them, but everyone else on calls can hear them. So I would like to apologize in advance. Yeah, thanks. So anyway, okay, let's kick it off today. Welcome everybody to the FPGA stand-up meeting for Open Research Institute for May 24th, 2022. What we do is talk about what we've done over the past little bit and what we are going to be doing over the next little bit. What we pick for the little bit is a week. If we have any roadblocks that are in our way, or if we need any resources in order to do the work. And we have a lot of different things going on represented by this group. So what we'll do is extremely briefly go around and give an update because what has been suggested for the agenda is exciting, and that is a demo by Leonard. So I will start. The past week has been chaos and lots of different things. The things most appropriate are some efforts in getting additional human resources for FPGA design. That's been successful. I'm looking for names to show up today, but I don't see any yet. But we will have some FPGA and ASIC designers that will be joining to help us out getting the encoder to work for the demo for August for DEF CON. So getting the encoder that Swatos and Everest have worked on, and other people have worked on too, to getting that working over the air and verified and validated. So progress there. Looking for more help, so you'll see it on Slack and in email. We have an opportunity for deep space to use our communications design. This is with a commercial company that's extremely interested in what we're doing. We have an opportunity to work at Leo that will crop up. And tomorrow is the release of the NASA SBIR and SITR solicitations for the next round. And I would really like for us to look at one, and if one of them guides our work and makes it possible for us to have some additional structure and goals, then we should do that. So the usual complaints are that I don't have enough time, and just like everybody else. And the roadblocks are non-technical, really. The hard part is never the technical part for what we do. All right, so next on the list is Anshul. And then when you're done with your report, pass it on to the next person that you see, and so on.
Sure. So for me, the progress is that now I can boot my ZC706. So I resolved the kernel issue, which I described last time. So I can boot it. Now I am stuck how to test the complete DVB-S2. Maybe it's because of my lack of experience there. So I have set up a time tomorrow with Everest, and we should be able to find a way forward, and I should be able to test it. I have everything on the board. Bitstream is there, kernel is there, everything is there, but I just need to test it. So that's me. Apart from that, I had a couple of meetings with Art and Bob to understand their software module and how I can proceed with that. The roadblock is that I need a transmitter device, which Art is preparing for me, and he will ship it over maybe next week. So yeah,
outstanding. That's good news.
Yeah, thank you.
All right, who's next?
Soto.
Hi, can you hear me?
Yeah,
Yes.
you sound great.
Okay. Well, thank you. Yeah, I couldn't get anything done on the past few weeks. I want to work on the on pilot insertion. I just need time to sit and go through. I haven't even touched my personal computer, so it's been annoying.
No problem.
Yeah. I'm gonna say Paul next.
Soto, 1 second. If
sorry.
I'm not able to catch hold of Everest tomorrow,
Mhm.
I will need your help to test DVB-S2 implementation. So I will ping you, and if you can just give me some time,
Yeah.
maybe on weekend or somewhere, then I need to get this done.
Yeah, no problem. Just let me know. Yeah.
Okay, thank you.
Cool. Sure. Thanks.
Okay, I guess it's my turn. I have nothing to report from the remote lab west here. Things have been just cooking along. I have a new Karapi shirt. Does anybody know a person named Monica who might be interested in the remote lab? I had a request, but it had no information in it. So anybody? Okay, I will ask Monica for further information to find out what she's planning on working on. That's all from here. Let's pass it over to James for remote lab south.
Paul mentioned, I'm James, Kilo Juliet 7, Kilo Delta Echo, reporting in from Remote Lab South. In similar condition to Remote Lab West, there's not really much that we've been encountering lately. No new strange requests. I'm sorry, I don't know of any Monica, and we haven't gotten any requests from that individual here. So things have just been doing as they do here, and not much else to report. I guess with that, I will pass it on to, has Leonard gone yet?
Nope, go ahead, Leonard.
Hey, how's it going? Okay, so I'm still, trying to figure out where I can fit in, but so I think I discussed with a couple of people last week. One of the things that I could do is so on for the receiver, we need a method of being able to get symbol timing and then also carrier lock. What's in chat anyways? Thanks, Michelle. Anyways, so I kind of dusted off some code that I had, and I added like the different constellations for DVB-S2. I'd like to share my screen at this point and then just show you what I have, and sometimes that can help, and see how you guys can use it. This is mainly for receiver stuff, but in general.
Yeah, good. Go ahead.
Okay, so screen 2. I have to warn you, this is not a finished product. And the other thing I have to warn you, it's combining 2 different visualization techniques. I was having problems with Plotly and trying to do it. Sometimes some of these things are just so complicated. They put too much, the works into the thing. Anyways, okay, so part of it's going to be displayed here in this browser, hopefully. Here's a code. I'm just going to run it, and then we'll talk to it, and then we can kind of explore sections in it. So just remember, the audience here, just it's to help guide the implementer on what potentially they could do for to achieve receive timing, symbol timing, and do what if scenarios. So this is kind of like an RF model, and in fact, I have various parameters in here. This is a single file here. I've renamed it DVS2 constellation timing and sims. So you can turn certain switches on and off. You can add impairments. Right now it doesn't. So I'm just going to run this for right now. And in debugger. So let's see here. Is this actually running? Okay, there we go. So one of the things we could do is I create a class called MD, which is for modulation, demod, whatever. And here you put in whatever constellation you have, and then you put your code rate. Only thing that this does with the code rate, it doesn't do any encoding or anything. I mean, any FEC associated with it. But on the 16 and 32 APSK modulations, the code rate will adjust the amplitude, and this does that. Anyways, so one of the things I do, I generate an IQ list for the constellation, and then I generate my data set. So I'll go ahead and just hit play on this thing. And one thing we'll do while it's running there, it's building out my visualization thing. Some of these figures that you're seeing at the bottom can be enabled or disabled, depending. A lot of it is just kind of for debugging of, like, let's say you go adjust something and you want to figure out what's going on. So that's what this is for. Okay, so it's kind of done this first thing here. Right now it's generating some other stuff up here. Let's look at these diagrams here. First of all, I put in, we could run this again in a second. I put in QPSK. This looks like a QPSK constellation, just in case anybody's wondering. The next thing here, figure 2 is our, one of the things we do, what this thing does, maybe I should kind of walk through it, is it'll generate your filters, and it generates two, one for essentially the transmit and one for the timing. So the just to kind of get you out on the transmitter, it generates essentially a single rate filter, kind of the what does Fred call it? The kind of the I forgot what the term is.
Multi-rate?
No.
Polyphase?
No.
Something
Anyways,
else?
he uses as a template to generate the polyphase. So I generate essentially the template, kind of the reference filter, and then I generate the polyphases, and I kind of overlay them. So this here is actual points, and this one here, the green, is actual reference, and then inside of that you see all the different phases overlaid on top of each other. So it's just kind of an interesting way to visualize what each phase looks like. May be useful, may not be, but the idea is that, you know, in here you can go in here and say, is that the same? You can go and zoom in on a data point or not. And then this is just for one of the phases, phase 0, what it looks like. And maybe it should have been dots, but it's connecting the dots. So we can just say that. So the reference shaping filter versus one of the phases. This is phase 0, what it looks like on one of the multi-rate filters. And then on the receive side, we need to do timing associated with that. And one of the things that we do, we oversample this quite a bit and generate a multi-rate filter. So this is kind of the oversampled kernel. And then this is the, oh, geez, damn it. Windows at its best. All the kernels overlaid on top of each other. So if we zoom in on this, we can see that it's a fairly high resolution, right? So just kind of the idea is that you want to get a fairly good representation of the data on the receiver, because once the data comes in, you're downsampling it to essentially 2 samples per symbol with this technique. All this is gotten from or modeled off of one of Fred Harris's, I suppose, either lectures or one of his, he kind of sent me over some MATLAB code. So this is a highly derivativized version of that, I suppose you could say. So after that, one of the things to get the phase lock loop to work, and also the symbol timing to work, we do a derivative filter. This is what that looks like, and it's oversampled as well. And then here's, if you take the derivative filter and the phases associated with it. So that's one thing that I should do. I should just bring up that presentation that he has, so we know where all these blocks fit in. Anyways, okay, here's one of the phases. And then this is the same thing, but just for the phases by themselves. So we can kind of look at that, make sure we're our filters are doing what we think they are. So that's kind of a visualization of the multi-rate filters plus the filter kernel that we use as a reference. This is done in matplotlib. If anybody knows Python, you know what I'm talking about. So the other thing we do, I had this thing, I'm kind of in the middle of converting it from Plotly to matplotlib. So Plotly, the nice thing about that, it generates HTML code directly, and you can set, it's a single file HTML. Each one of these is a file associated with it. You can see the file name there. So all the data and everything's in there. The HTML files are a little bit on the large side for an HTML page, but the idea is that you can, it's very interactive. You can go in there and you know, look at data points. So let's say if we want to say, okay, let's zoom in onto this thing here and see what's going on at the very beginning. And let's see here, this is going to work. First of all, maybe not. Okay, well, maybe too many data points right there. Anyways, okay, so here's just the data. There's 4,000 symbols going through. As part of how the multi-rate filters work to recover your symbol timing, one of the things you do is you generate this instance or implementation has 32 phases, right? So I take each one as the data goes through it, and you can kind of look at the data as it goes through the phases, and you'll see what happens is that one of these is going to kind of represent the best sampling point for the data. You see, like the data here lines up here, and your midpoints are more or less in the middle here, and whereas on these other ones they're not. So the steps 23, 24, 25 are interesting to note, because if we look at so these two diagrams look pretty much the same, and that's because one of these is using L filter, and then one of these is using an algorithmic approach. And I wanted to compare the two to make sure that they were the same. So, and they pretty much are. So the algorithmic approach is what essentially goes into the FPGA once you code it up correctly and whatnot. All right, down to brass tacks. Okay, so here's a symbol timing, and you see, you know, I start the simulation, there's a rollover crossing boundary, then there's a loop response, and then it settles here, right? And then this is the derivative filter on you know what it thinks the values are. Let's see. Oh, so here it decided to zoom in. This is, you know, so you have these little tools here: zoom, pan, whatever, lasso, auto scale. This is all in HTML land, so it's kind of interesting to have the Plotly stuff represented. And then not only that, you can, let's say we zoom in on a section here. You can look at these values pretty easily, and then there's also added information that you can display on these little tag values. You know, the tag that sticks off to the side. In machine learning, you know, there could be a lot of them. You plot it with respect to something, but then you can have a lot of extra information on there. Here, it just gives you your coordinate, you know, basically X, Y coordinates. So that's one advantage of using Poly. Okay, so here's the loop response. You see it has its response and it settles out. So this is pretty good, actually. And then, so I plotted a pre and post. It says PLL here, but I think this is symbol timing, I believe. Maybe not. And then here's our constellation that's getting recovered here for the QPSK. You see there's a little spread here, not exactly very good. Okay, so this is requires a little bit of debug. So that was a symbol timing. So along with symbol timing, you also need to do carrier lock where there's symbol timing and then there's what do you call it? Just timing. It's mainly carrier lock. All right. The phase lock loop here. I mean, these are pretty small numbers, but you see it just doesn't settle, and then here's your error here. So,
Yeah.
Unfortunately, one of the reasons why I'm trying to convert this over to matplotlib is because when you're graphing multiple traces like this in Plotly, I cannot set the axis over here, so it automatically zooms in onto the excursions of what the data is. Anyways,
yeah, there's no way to manually override the limits.
I'm sure there is. I don't know how.
I don't know either. I've run into this before, but I'm not that experienced with it. So you have our empathy.
And then here's the post PLL on that, which for some reason it looks like it's being plotted over here or over here as well. I don't know why that is. And then here's a constellation. Now, because we're downsampling to 2 samples per symbol to do all of this, and I don't know if this is a Garner or early late, whatever. It's one of Fred Harris's things. So you have your even samples or your odd samples, depending on how it starts off. One of those even samples are going to be your actual symbol data, and the other one's going to be the intermediate transitions, between symbol. QPSK here, obviously, you have these odd ones here are basically the ones that don't change, that stay at this coordinate point. And these here are when it transitions from this guy over to this guy, you get these in the middle. And then anything going across through the middle is obviously, kind of going through the center points. So you see these are the odd ones. So at some point, you'll have to, the design will have to make a determination. Do I use the even ones or the odd ones? Okay, so that's that. Let me go ahead and clear this. Obviously QPSK is not exactly, damn it, sorry, keep that out. QPSK is not the most exciting thing, so I'm gonna go ahead and change this to, let's say, 16 APSK, and then stop that simulation, and then let's rerun it. Anyways, while this is running, let me kind of quickly go through the code. So the code, run, come on, just go. So I create a class, modulate, demodulate. My brain's not smart enough to come up with a snappy name. So it goes through its init function. So in here, I give it the tables. Okay, it's done. So for each, modulation, there's these are dictionaries in Python, if you guys don't know. So the first, and each one is, the key value is just the index for the modulation number. There's 4 in QPSK. And then each entry in the dictionary, the first entry is just kind of the ring number. So there's for these guys, there's R0, 1, 2. There's 3 rings basically. And because it's 0 based, if we look in the well, let me bring up the one second. Let me bring up the if we look into the Etsy org doc, you have your constellation, and then you got your code rigs and so this table is essentially in the in the code that I showed you. I'll show you where. And so you have your different constellation points and your gammas here, which determines what your ratio between R2 and R1 and R3 and R1. And like in the case of 32 APSK, there's this inner one here is R0, R1, and R2 is here. In this document, because this is based off, they don't think 0 is a number. They say this one here is R1, 2, and 3. I probably could have done the same, but I just figured it's just easier for my numbering system. If you want to change that, let me know. Anyway, so these numbers here represent, this column represents the ring it's on, and then these are the angles that it's on. And some of this I got from Andre, I believe. I just kind of, anyways. And then I say, okay, well, because there's a amplitude with respect to gammas change based on the code. So that happens here. And these guys here, these are dictionaries as well. And then there's the class itself, the instance of the class has essentially the modulation, default modulation is QPSK, but you just set that whenever. Code rate, that's one of those numbers down there. And then some other stuff, I forgot what this is, but if I wanted to save some. So I generate a magnitude list, and then I generate the constellation, and then in the generate file, this is where I do my polyphase and filters and derivative filters. Let's see here. This is a debug flag, so if you want to see those things, you can. Okay, there's generate data. So in generate data, basically, I go in there based on the constellation. It tells you how many data points there are, and then I generate this thing. So I'm just basically generate random data, and then between, let's say, 0 and how many points are in the constellation, and I return them. That's what you're seeing. Okay. Simulation's been finished, so let's look at those things there. So again, this is what goes out. This is after it's been kind of double filtered, I believe. And then you know, this is the kernel again, and we've been through all these filters here, but they're the same filter, just, you know, this is a derivative filter with all the different phases in there. Okay. And then here we look at the data. We can look at the data here. This is the data prior to filtering, and then this is the data after it's been upsampled and filtered. And let's see if this will actually zoom in this time. Yeah. So one thing that Plotly has is a problem when there's too many data points in a plot. It takes too long for it to do anything, and we see that right here. It's just not very reactive. Anyways, it's normally you'd be able to zoom this in. Matplotlib doesn't have this issue. That's one reason why I'm going back to Matplotlib. Okay, so here's a filter again, the slider. So, you know, at some point, this is multi-level. That's why we get these weird shapes. And there's another one using the algorithmic polyphase filter. Again, here's a loop. Here you see it acquires the symbol timing, and then it kind of saves log to it there. I haven't done I'm not changing the phase in the middle, so that's one thing we could potentially do is massage this for that. Data, this is the recovered constellation. So one thing that I like to see is these sampling points to be a little bit better. This is, you know, the simulation without any noise added to it. So this concerns me a little bit. These should be kind of, almost as good as these guys here. And these guys, you don't see any noise on this at all. The variation here, I believe, is due to the phase arm. You got to imagine it's toggling between a phase. If you go to, let's say, this thing here, and let's say we just zoom in on somewhere in here, and even if we so you see there's algorithmic noise here, so it's toggling between, these are quantized, right, between phase arms. So you have phase lock loop for the symbol timing loop, I suppose. You go on between +1, -1, and kind of averaging out. And if you remember, you're on, let's pick one of these things here. Imagine you're on one of these phases and you're selecting between a couple of them, right? So you're toggling between a couple of these things. So that the gain, remember how these filters work. You have everything in the thing, it's all added together. You convolve it with a data point and a couple. So the numbers vary, essentially is what I'm saying. What's going on here? Okay, so we see a little bit of noise there. Okay, so this here is essentially, I believe it's a symbol timing, and we see the phase lock loop response. How do we get back to? Looks like what you would expect. Now, when I go to do my frequency lock, this isn't obviously. It's like my parameters for that is it's not. I like to see this kind of just go and stay. We should see something similar to this here, even if we zoom in. If we zoom in on this guy here, it's there's a lot of wander here. I think. I mean, I could see if it was just kind of wandering or noisy right in here, but I mean, you zoom in here and shit. You zoom in to these data points here, and they're not wandering that much. I mean, they're not noisy. They're not like impulse noise wise, but the whole thing, the whole thing is just wandering. So there's an issue there. Somebody or me or somebody's got to look into that.
Well, I mean, the excursions are the excursions really pretty modest?
They seem to be fairly small, but I mean, I just don't like the place. There's a way to, there's something wrong with it.
Yeah,
anyways,
what you're saying is you'd like to see better behavior.
Yeah, it's unstable at some level. There's a little bit of oscillation there. So here's the symbols after the timing recovery. I believe, which one is this one? This is the symbols after the symbol timing. So remember, this is just nor if you let this run right without the if you add in an impairment in there, like a frequency offset, these right now this simulation is not run with it. These points are going to be spinning. Right, you're going to get a circle here. You'll get a ring here, and you get a ring here. Right. It's not until you get to this guy here when you do your carrier recovery that they stop spinning, right? Because at that point it's locked to the carrier frequency, and as long as the carrier frequency is rock solid, these things aren't going to move. If the transmitter has a little bit of wander in the carrier, you'll see, depending on the loop response of this received PLL, you'll see some wandering here.
Right.
Anyways, here's your odd even again, right? Where in this case here, the even ones are your actual symbols, and the odd ones are the transitory signals that go in between there. Anyways, that's the model. I kind of want to put it up in there and you
Yeah.
know, hopefully it's useful for somebody to use. The idea is that once you get carrier lock, these symbols here go into the decoder. You know, you've achieved symbol timing and you've derotated the constellation and locked it in place. That's what this would represent. And then you put that into the decoder, and hopefully with any kind of luck, you get your data back or video, whatever you've transmitted. Anyways, does that make sense? Does anybody have any questions, comments, questions, suggestions? I open it to you guys.
Yeah, yeah, it makes sense to me. That's fantastic. This is very exciting to see, and it moves us solidly towards starting to model and look at receiver. So yeah, Anshul and Sawato had to go, but they are very interested in the rest of the recording and I think talking with you more. Everest also said that he couldn't make today, but he's looking forward to the recording, and I'm absolutely sure that he'll be interested in this as well. So yes, I think you should put this code in the repo. And I think you had some questions about what how to license it. Is that?
Yeah, well, I was just wondering what you wanted to use.
Yeah, so the default for all of our work is GPL 3.0 for software and the CERN 2.0 license for hardware. But any other license that you need to specify, we're totally open to that.
Yeah, this is probably, it's not considered hardware because it's not like HDL code, right? This is a Python model.
Yeah, so yeah, it would fall under, but what if GPL 3.0 is fine to you, then that's what we default. And then if you prefer something else, then that's what we use.
Okay, so so that's GPL.
Yeah, and I think if Paul or anyone else has some comments to help figure this out, they'd be welcome.
Okay. I remember Linux Torvalds was complaining about GPL 3.0, I believe, but
Yeah.
he wanted to stick with 2.0 or something like that. I don't remember what the reason was, but and I'm not real smart on those things anyway. So I think
Yeah, and I'm just here to help. So somebody that
Yeah.
actually knows might be good.
Yeah, Paul, you want to chime in on what your thoughts are?
Yeah, if you don't care, you might as well choose the ORI defaults. GPL3 differs from GPL2 in that it has stronger protections against using the software in hardware. So if you care about people being able to make copies of your thing and sell them, then GPL3 might be preferable. But
Yeah, this is not you know, it'll never be run in hardware, obviously, or productized. It's mainly it's a development tool, like for somebody that's generating hardware or HDL code. Hopefully it's like MATLAB, basically, essentially is what it is. You know, it's I'm using Python now because it's easy to get, it's free. I don't have to learn yet another language.
yeah, well, if you want to get smart on licenses, there's tutorials I can point you at. But if you don't care about that, then just take the defaults.
Yeah, which is GPL 3.0.
Yeah.
Okay. I don't have anything else.
Wow, well, that was plenty. Thank you so much. And we'll get it into the repo and talk about it with the team on Slack and in our weekly report. All right, anybody else with work that they've done over the past week and work that they have scheduled over the next week and roadblocks and resources needed, speak up.
I have a question. If anybody can hear me, hopefully.
Yeah, go ahead.
The thing that I was mentioning last week, which was spectrum analyzer stack, and just basically using it, hopefully for seeing the spectrum and measuring levels. do the labs already at ORI have their own spectrum analyzer kits that you're interested to do that, or that'll be later in the development process?
We do have spectrum analyzers at both labs.
Okay, and our output range is in the 10 gigahertz band?
Yeah, we're not able to cover that with the spectrum analyzer we chose. But you probably do most of the work at IF anyway.
Oh, okay. All right. I'm actually asking because I'm just for my own use case. I'm making some test boards. I've got designs in progress, but just basically try just generating a carrier and just doing on-off keying basically, and seeing them. So I thought I'd just sync with your future requirements just in case you wanted to get another report.
Oh yeah, no, sorry, not to cut off Paul or anything, but the higher than 6 gig, which is where our spectrum analyzers top out at, would be welcome. So whatever you got, we'll use. We're looking at, well, we have a dual band feed for 10 gigahertz / 24 gigahertz, which we're sending out to people this week. And we're looking at 47 gigahertz. So, we'll need measurement at the higher frequencies. So anything that you have that's a resource is welcome.
Okay, I've sent you an email. It's in your mailbox, Michelle. But generally, the up to 22 gigahertz I'm already set. So the question is, what levels, what kind of things would you like to see on an analyzer? I mean, we can reduce the power until we can't see it. I'm just curious, what would be the kind of test requirements? I just want to follow a program if somebody's come up with it.
Oh, gee. I don't know. That's a good question. Paul, do you have any comments?
No, I don't think we have anything detailed out for that. It's Wally may have had some thoughts, but those thoughts are lost.
Okay, so in the future, do we have to go through a qualification or a certification stage for permission, like when we eventually go for mission?
Sort of. I mean, the requirements for any particular mission are going to be obvious to us. So, for example, requirements to go on the upcoming sounding rocket missions are obvious, and there are gates that we have to pass at these various things. And then to actually be on a mission, there's going to be rubrics and credentials and qualifications and test schemes. But as far as our own internal, I mean, because that's what you're at right now, is like, is there anything internal? And it is, set up something that you can be calibrated to some level, and
Yeah.
just present the level, like say, this is going to get you within 1/10 of a dB, and that's fine. That's going to give us more than enough leverage.
I can do something a bit more than that with
Oh,
the
good.
existing setup, which is
Yeah. So I mean, I'm just throwing out there, because like a
Yeah,
1/10 of a
yeah.
dB would be for a normal, like a typical benchtop. But what you're talking about with the equipment that you have is a little bit better than that. So I mean, it's just simply a question of communicating. Here's what I think the calibration level is. Here's the last time I was calibrated, just to be transparent. And then I think that that's good enough, and that's super helpful.
I think I can create the mask. I mean, I can report the side lobes. I mean, from a center frequency minus and a center frequency plus, I can write an automation script using these bench measurements and actually sweep and give a test device under test, basically a report that it's generating such and such RF at such and such points away from center frequency.
Oh yeah, no, that's a slam dunk as far as I'm concerned. For our purposes, for internally, we just do good faith. So we just make the best good faith effort that we can.
Yeah.
And then when we move towards any particular mission, there will be external requirements that we may have to encounter and deal with. And if we do a good faith effort internally, then we'll have the flexibility and the ability with the designs that we have to surmount any challenges that we get.
I've read somewhere that spurious radiation is a big concern when you're the transmitter person team. So eventually, if you give it to for integration, they want to know that, okay, you're not broadcasting XYZ products.
Right.
harmonics. So I just this
Yeah.
equipment is expensive enough that it's
Right.
heavy enough. Let me put it this way: it's not expensive,
Yeah.
it's heavy enough. Okay.
Yeah. I
The
think you're
floor is
totally.
buckling with the weight.
You're just, yeah. Oh dear. You're on the right track, and we'll
Okay.
let's go get some
Yeah,
traction on this.
put me on that track, please. I just need
Sure.
to see the standards. Like there are EMI, RFI, RF, whatever RF compatible. I just need to see which standard you're shooting for, and then I'll derive the matrix and present it, if that's okay.
Okay. Yeah, sounds like a next step.
Okay, thanks.
No, thank you. That's deeply appreciated. All right, everybody. Any last questions or comments before we close for the week? Thank you, everybody, for coming to the stand up. See you on Slack and online, and see you next week. Same time, same place.